All right, we're on Unit 4, Calculus, Day 3334 Notes, Part 3. And what we're trying to do is with the relationships we've been talking about, going from the original function to the first derivative to the second derivative, we now want to start being able to make some decisions or make some conclusions based on what we've done. So now, if we're given some information in the second derivative, what does that mean? And we'll try to work backwards here and go to the first derivative and then go backwards to the original function. So let's do that now. Okay, so if the second derivative is 0 or is undefined at x equals a, then I know the first derivative has a potential relative max or min. And again, if I have a max or min, what's the derivative of that? The derivative 0, okay? Or it could be undefined when we're talking about a cusp or a corner. So that's just going back one derivative. Well, now when I know that my first derivative has a potential max or min, then the original function is going to have a potential point of inflection. And what is that good for? Now when I know the second derivative 0 is undefined, there's a potential for a point of inflection. And later on we'll figure out how we can determine that. Okay, if the second derivative is greater than 0, well, I know the first derivative must be increasing, and wherever the first derivative is increasing, that means the original function must be concave up. So what can I now conclude? If the second derivative is positive, then the original function's concave up. And in the same way, if the second derivative is negative, then the first derivative is going to be decreasing. And we knew that when we were going from the first derivative to the original function, or the original function of the first derivative. Now we're just talking about it between the second derivative and the first derivative. Well, now we're starting to learn if the first derivative is decreasing, then the original function is concave down. Okay, so the conclusion is if the second derivative is less than 0, then the original function is concave down. Okay, now if the second derivative changes from positive to negative, then the first derivative is going to have a relative maximum. Same thing when I went from first derivative went positive to negative, then the original function would have a relative maximum. No, that's true from the second derivative to the first derivative. Well, and if I have a relative maximum, then this is going to have a point of inflection. So we talked up above that there was a potential point of inflection if it was 0 or undefined, but now if it goes from positive to negative through that 0 or undefined, it's going to have a point of inflection. Okay, and I know the first derivative will be a relative maximum. Okay, and same is true, or a little bit different, when I change from negative to positive in the second derivative. We're going to get the first derivative is going to have a relative minimum, and once again, as long as it goes from negative to positive, if that value was 0 undefined, I'm still at the original function going to have a point of inflection. Okay, on a previous section of the notes in a different video, we found that the first derivative of f of x equals x plus 2 to the 2/3 plus 1 was the function f prime of x equals 2 all over 3 times the cube root of x plus 2. Now we want to find the second derivative and then do a sign change chart or sign analysis to determine intervals of concavity and points of inflection, possible point of inflection. Again, let's verify our analytical results by looking on the graph on the previous page. Okay, so the first thing is to rewrite this as a polynomial. Um, so I'm going to do second derivative is equal to, so 1/3 times 2/3 is, oops, and I forgot, that's going to be negative 1/3. So negative 1/3 times 2/3 is going to be negative 2/9. So chain rule, going to tell me to do x plus 2. Subtract 1 from negative 1/3 is going to put me at negative 4/3 times the derivative of what's inside is just going to be 1. And now let's rewrite this. So it's going to be negative 2 all over 9 times the cube root of x plus 2 all to the fourth. Okay, so that's the second derivative. So what do I need to do? I need to do a sign change chart. Second derivative. And I'm going to find out that, hey, what's going to make this 0? What's the critical value? It's going to either make it 0. Well, nothing's going to make it 0 because that's when the numerator is 0, but it's going to make it undefined at when x equals negative 2. So let's now come here. Let's pick a number a little bit less than negative 2. I'll pick negative 5. What do I get? I get a negative 5 plus 2 is going to be negative. To the fourth power is going to be positive. Cube root is positive. Times 9 is positive, but then negative 2 divided by that positive number is going to be negative. Okay, and then we just said, hey, this is going to be undefined right here. And now let's pick a number bigger than negative 2. Let's pick 0. 0 plus 2 is positive 2. To the fourth is positive. Cube root is positive. Times 9 is still positive, but then negative divided by positive is still negative. Okay, so what does this tell us? So what can I conclude? So I can conclude that the original function is concave down on the interval from negative infinity to negative 2, not including the negative 2, and negative 2 to positive infinity. So pretty much everywhere but when x equals negative 2. Um, why? Because the second derivative is negative. And, and the original function is never concave up because f double prime of x is never greater than 0. And lastly, the original function does not have a point of inflection because the second derivative never changes signs. If it had gone negative to positive, then it would have a point of inflection, but it doesn't. Okay, next problem. Given the equation of the derivative, determine the intervals where the graph of g of x is concave up, is concave down, and determine the x values of points of inflection. Show your analysis and give your justification for the answers. So I'm given the first derivative. I got to find the second derivative, which it's set as, I'm going to need the quotient rule, do some simplifying. Once I simplify, then I want to do a sign change chart, and that will help me, that's going to help me figure out, again, where it's, the original function's concave up, concave down, and any x value point of inflections. All right, so let's do that. Second derivative. So using the quotient rule, Hody high, that means write the denominator, x to the fourth plus 6x squared plus 9 times the derivative of the numerator, that's negative 12, that's just multiplication, minus Heidi ho, so that's the numerator times the derivative of the denominator, 4x cubed plus 12x, all over the denominator squared. Um, and that's going to be x to the fourth plus 6x squared plus 9 all squared. I'm going to rewrite that a little bit differently the next step. Okay, so distributing the negative 12 and distribute the negative 12x, and I got to pay attention to the sign up here. So I haven't combined anything. Now, real quick, over here at the denominator, hey, that's a perfect square trinomial. That could be written as x squared plus 3 all squared. And so now when I take that and I square it, it's actually going to be x squared plus 3 all to the fourth. You may or may not see that. Hopefully you do. Again, anytime you see a 1 and a 9, ooh, and you think of the middle terms, twice whatever number is being squared. So square root of 9 is 3, and that's 2 times 3 is 6. Hopefully you're seeing that perfect square trinomial. So now let's combine like terms and then start trying to factoring, see if we can cancel anything out. Okay, so you can see a couple steps that I've done to simplify. Now we can cancel out, hey, I have an x squared plus 3 here, and I have 4 of them down bottom, so I can just rewrite that to have 3 of them. And so I am left with 36, and the x squared minus 1 is a difference of squares, so that's x plus 1 times x minus 1. And now down here, I have x squared plus 3 all cubed. Okay? So now let's look at this second derivative and let's find out what values make it go to 0. And I can quickly see that, hey, when x equals plus or minus 1, the second derivative is going to go to 0. So this will be helpful for finding when it's concave up, concave down. So those are, let's put in, so this is my second derivative of g. I know I have negative 1. Hey, that goes to 0. And I have, let's put positive 1 right here. So let's do our analysis. Um, let's go a little bit to the left of negative 1. I'll pick negative 2. So let's come over here. I'm going to get 36 is positive. Um, negative 2 plus 1, that's going to be negative. Negative 2 minus 1, that's going to be negative. So my whole numerator is going to end up being positive. And then down here, negative 2 squared is positive, plus 3 is positive, cube is positive. So this whole thing is going to end up being every value over here is positive. We'll talk about that in a second. Let's pick a number between these. Perfect. X equals 0. So I get 36 is positive. 0 plus 1 is positive. 0 minus 1 is negative. 0 plus 3 is positive. Cubed is positive. Okay, so here is negative. And let's do positive 2. So 36 is always positive. 2 plus 1 is positive. 2 minus 1 is positive. And then a positive squared is positive. Plus 3 is positive. All of the third power is positive. So this is positive. So that's going to tell me a couple things here. Okay, so now let's look at what conclusions we can draw. Well, I know that the original function is going to be concave up on the interval from negative infinity all the way to negative 1, not including the negative 1, and then again from 1 to positive infinity because the second derivative is positive, and then the original function is going to be concave down on the interval from negative 1 to 1 because that's where the second derivative is negative. So again, second derivative positive, original function's concave up. Second derivative negative, original function's concave down. And now I know g of x is going to have a point of inflection at both x equals negative 1 and x equals 1 because the second derivative changes sign at negative 1 from positive to negative, at positive 1 from negative to positive. Okay. Okay, so now the second derivative is primarily used to determine intervals of concavity and points of inflection. It can also be used to identify relative maxes and mins of a function. So if we know the second derivative, we can use this test to find out some information about maxes and mins of the original function. So the second derivative test, an alternate way to identify relative max and mins using the second derivative. So if x equals a is a critical number of the original function f of x, then the derivative at that given value a equals 0 or is undefined, making x equals a potential max or min. Okay, so again, we have to know that it's a critical number of the original function, and then the first derivative, when you put it in, equals 0, or makes it undefined. So if the second derivative with that value a is positive, then the original function's concave up, and if it's concave up, that's going to make the original function a relative minimum. Okay, and let me just quickly draw that. So that's concave up, a quick little part, therefore it's a relative minimum. If second derivative at a is less than 0, then f is concave down at x equals a, which again, the original function is going to be concave down, which that then tells us the value x equals a is going to be a relative maximum. So that's an example of something that's concave down, and we have a maximum. And then lastly, if the second derivative at a is neither positive nor negative, then x equals a is not a relative max or min. So that is the second derivative test. Let's go to that last page and do these two examples. Use the second derivative test to locate and classify all x values of relative extrema for each function. Okay, so they're giving us the original function, so I need to find the first derivative. Once I know the first derivative, I'm then going to set this equal to 0. that's going to be, I can factor out, what can I factor out? 4x squared. So I'm going to have x minus 3 equals 0. So then two things multiplied together, at least one of them must be equal to 0. So I find out, hey, x equals 0 or x equals 3. Again, using the second derivative test, I had to know where the first derivative was 0. So now let's find the second derivative. And that's 3 times 4 is 12. So I get 12x squared. 12 times, oh, that's supposed to be an x squared. 12 times 2 is not 12, but 24. And that'll be 24x. And I can factor that out. I guess it doesn't matter either way, but it might save me some time because I really just need to know if it's positive, greater than 0, less than 0, equal to 0. So 12x, so I get an x and I get a minus 2. Okay, so there's my second derivative. So now what I'm going to do is I'm going to take that, red, take that second derivative and substitute in 0. And then let's also substitute in 3. So when I substitute in 0, I'm going to get 12 times 0 times 0 minus 2. 12 times 0 is 0 times anything is 0. Over here, when I substitute in 3, I'm going to get 12 times 3 times 3 minus 2. 12 times 3 is 36 times 1 is 36. Again, I'm really just worried about whether it's positive or negative. So since the second derivative at 0 equals 0, then x equals 0 is not a relative max or a min. And since the second derivative at 3 is greater than 0, positive, then x equals 3 is a relative min of the original function. So let me write those out. You can copy those down. Okay, those are the conclusions we just stated. All right, last one. We got to do the same thing. We got to find the first derivative. We got to set the first derivative equal to 0. We got to take the second derivative. We got to put those values in that we found for the first derivative into the second derivative, see if it's positive or greater than 0, less than 0, or neither of those, and then make our conclusion. Okay, so when I take the derivative of f of theta, derivative of cosine is negative sine, so I get negative 2 sine theta. Derivative of negative theta is negative 1. Let's set this equal to 0. Let's add 1 to both sides. Negative 2 sine theta equals positive 1. Let's divide both sides by negative 2, so I get negative 1 half. Therefore, inverse sine on each side. 1 half is going to be pi over 6, but it's negative, so it's going to be, and again, it's only from 0 to 2 pi, so it's going to be in the third and fourth quadrant. So pi over 6 is 30, so it's going to be 210 and 330, which is 7 pi over 6 and 11 pi over 6. Okay, so that's where the first derivative equals 0. So let's now take a look at the second derivative. So my second derivative is going to be equal to negative 2 cosine theta. And the derivative of negative 1 is just going to be 0. And so now, what do? Every place I found where the first derivative was 0, I'm going to substitute that into the second derivative. So that's 7 pi over 6. We'll find out what that is. We'll do second derivative of 11 pi over 6. Okay, and I get negative 2 cosine 7 pi over 6. We said that's 210. That's in the third quadrant. That's going to be a negative value. We know negative 2 is negative, so hey, this is going to be positive. That's really all we're looking for. And then here is negative 2 cosine of 11 pi over 6. Really, that's 330. That's going to be in the fourth quadrant. That's positive. Negative 2 times positive. Oh, that's not equal to 0. That is less than 0. Okay, so if I know the second derivative is positive, then I know I'm going to have a relative min. And if I know it's negative, I know I'm going to have a relative max. So let's write those up. Okay, so at 7 pi over 6, I'm going to have a relative min at the original function. Why? Because the second derivative is positive. And at 11 pi over 6, I'm going to have a relative max because the second derivative is negative. Again, second derivative negative means it's concave um, excuse me, is less than 0, then I'm going to have, and I wrote that down, um, is concave down, which means I have relative max. And when here the second derivative is positive, which means concave up, which means I'm going to have relative min. Again, let me just draw those so we can visualize what we're talking about. Again, positive means concave up. Here's an example of something that's concave up. Look, I have a minimum. And down here, second derivative is negative, means concave down. Something concave down looks like this. That means I'm going to have relative max. Okay, so that's the second derivative test. Make sure we finish that up, and we will take a look at the